All right, so this is video 3 of class 7. We got done talking about the material derivative and Reynolds transport theorem, but now I want to try to use it for something because it is really just conceptual and it's not a whole lot of fun. But here's a slide from Sengel's book describing sort of this interchange of the material derivative and Reynolds transport theorem and how they're kind of related to each other. So the main thing that we want to try to look at first is the conservation of mass, aka the continuity. In this case, the big B is going to be equal to mass. And so maybe I should move on to this. So the big B is, I put a big M right in there. So little b is m per m, or just equal to 1. So what we're going to say here is the integral, or the derivative on the control volume. Now all of a sudden that little b becomes 1, and times the density times the volume, incremental volume, and we take the integral across the whole thing to get the total volume. And so that's kind of understandable that this right here is going to be mass, the total mass as it changes with time. That's within the control volume. And over here, here's the integral as they're passing in the control surfaces where the little b is 1. And then we're going to take the density and now the all-important dot product of the velocity and the outward facing normal vector. And we're going to do it over areas right here, right? So by definition, mass is conserved, right? So that's equal to 0. So we could write out this as a continuity equation. I'm not sure it's necessary to repeat it, but might as well because it's the definition of the thing. Here's the control surfaces, and we hit the density times the velocity vector. Once again, it's dotted against the outward normal, dA equals 0. So if we say the continuity equation, here's the more mathy version of the thing. We'll write it in a second. Is probably the way that we want to remember it, right? The simple one. So just noteworthy, this can be rewritten many simpler ways, but this is like sort of a big picture. Remember that dotted thing really was just establishing the positive and negative, right? So we could see that when we dot these and they are going opposite directions, they're going to be less than zeros. Therefore, in is negative. And when we dot them there, it's going to be greater than 0. So it's going to be positive outwards. But remember, even if this surface is if the part of the velocity that is not perpendicular to the control surface does not count, if we wanted to make it in math. Now, for steady, just simplifying assumptions here, if the control volume doesn't change, if its size doesn't change, or if the mass inside it, I should say, doesn't change, then we're going to have steady flow, which means that del T right here, that goes away. And so what we could do is we could just, well, I guess I'm going to write that out. Okay, so that's going to go away, that part, that integral d volume, right? Remember, that's d volume, and it's across the control volume. That's going to be equal to 0. So the steady flow you could think of as the accumulation or deterioration, right? So if we go back to that one analogy that Dr. Foley from the Coast Guard Academy had, we could have like our Colosseum, and we could have chariots coming in and out. And here's a little pony here, not a very good one. Hey. So here's our stuff. These are our gladiators, and here's our accumulation of gladiators. And here is a chariot coming out. So these are the transporting things that are coming in and out. These little horsey carriages. And here's the stuff that's coming in. Well, if the mass is the stuff, mass is obviously transporting mass. It's sort of self-referential here, but mass is if these two are different from each other, like if this one's greater than this one, that means they're going to get bigger and bigger, the amount of mass inside the control volume, and vice versa. So If that's not true, therefore we have steady flow, right? The amount of stuff that's been, or in this case, mass that's accumulated inside there. So it's if that's the case right here, this is redundant. I don't know why I have this, but I'll write it anyway. Not redundant, but it just kind of communicating, right? Just emphasizing, repetitious maybe, yeah. Okay, so but if this is the case, if the steady flow is the case, but if it is steady, then we have just a very simple thing where we say the sum of all the outwards mass flow minus the sum of all the incoming is equal to 0. And that is, in many ways, the thing we should think of is the continuity equation, right? It's only the instance in which we're accumulating or deteriorating. Now, how could we deteriorate in this? Well, this guy could be more. We can also have a term where if this were to not be 0, right here, this portion of this, that would be more like a nuclear thing where we're turning mass into energy, or somehow going the other direction, turning energy into mass, right? But we assume that we're not playing with that kind of physics, and we are just dealing with the everyday kind of stuff. Now, a notable thing here, if it's incompressible, if density is constant, right, we also could say that we could have the volumetric flow, right? So this would be cubic feet per second, or, and we're putting a dot on top of that, or it could be gallons per minute, or what have you. To be that is also true as long as we're incompressible. I think my office hours are starting here in a minute or two, so I'm going to wrap it up here with this video before we get to any examples. They're kind of boring examples, maybe. Well, we'll see. So we have the average. Something we should notice that the average velocity is a fair assumption to make, or sometimes a useful assumption to make to try to make solving problems easier. So I'm going to use a v bar, which does not mean the vector of the velocity. It means the average velocity. So it doesn't have a little arrow on the end of it. That's what we mean by this. You could take across the area right here and take that. This one is a vector hat, and dot it against this, right? And dA, right? So I guess maybe we could say a particular cross control surface. So it doesn't necessarily over all control surfaces. We're talking about a particular, and we could divide by the density times that area, and that's going to give us an average, right? We could probably just put AVG underneath it. So that's just very helpful to us, like that we can, and then I say, so this is equivalent to the velocity of a uniform profile, right? So most velocity profiles are not uniform, but we could say, let's just pretend that it's uniform across the entire surface, and therefore we can find a average velocity, and that's what we probably use most often. These are just reiterations with not a whole lot of differences, just a little incremental. I'm using another book, so numbering examples doesn't help us a whole lot. But if we have, this is the non-deforming control volume, and yeah, I don't know if what it was I wanted to necessarily say about there, but it says there are 5 examples in the book, and I don't think that's not the case right here. I think I did upload those, by the way, to Blackboard. So if you wanted to see those examples, because I make reference to them, I put them in there. It's just for your own edification. Most problems that we are going to use this for are very simple, straightforward problems. So we don't have to spend a lot of time on this particular topic. Okay, so here is the accumulation term right there. So they're keeping it. They're just showing this. If it's a non-deforming control volume, somehow I can think of the density would actually have to change, right? So if it's a non-deforming thing for any accumulation to be happening. So this remains a little bit generic. It doesn't have those specifics of the previous equations that got written down, so this is not a continuation of that. A moving non-deformed control volume, which would be like a gas turbine or whatever. We have to be careful. We can use the relative velocity now instead, because that's actually, it's the thing that will represent the mass flow, the actual mass flow coming in and out. So you have to watch out for the velocity of the control volume will determine that. And a deforming control volume, we might also, I don't really see too much of a difference between these two equations right here. No, I don't see. I think it's just what the relative velocity is. No. Well, this is the one, this is a situation where we would have this right here, right? Where if it's a deforming control volume, we would definitely have to consider how the balloon is getting smaller right here with time. So maybe that's a worthwhile thing. All right, so I'm going to, this will be end of video 3. This was not a great video. All right, well, we'll keep going. Gotta have a full set.